This is the Decision 1 exam from 2023. Let's just go ahead and do it. Eulerian, semi-Eulerian, or neither. Well, it's actually got three odd nodes, I think. This one, and this one all have odd degree. So it can't be either Eulerian or semi-Eulerian. Eulerian would be no odd nodes, and then semi would be two of them at most. Write down a value of Hamiltonian cycle. Well, I mean A, B, C, D, E, A. Sure. Is it planar? Yeah, you could put this node, this arc out here, and then nothing would cross over. I would suggest that you actually draw it, but I couldn't be bothered. State the number of arcs that would need to be added to make K5. Well, K5 is just a complete graph with 5 nodes, so you need to add an arc from E to C, and you need to add one from A to D, and those would be the only two that you need to add in. And that would be 2 extra arcs there. We've got a table going on here, and it wants us to do Floyd's, except it's done lots of Floyd's already. It just wants us to do the last one, looking at E every time. So, okay, well, obviously the E row and column aren't going to change. That's fine. Oh, no, it wants us to learn the initial time matrix first. Sorry. So A to B is 10. And of course, because this is not a directed graph, this is going to be completely symmetrical. So that's going to save us some time. A to C is 15. So that all can go there and there. It's both directions. And then A to D we can't do directly, right? That's one of the missing arcs here. So we just have to refill that as infinite. And then likewise, we'll just keep going. A to E is 5. That fills in both sides. C to B is somewhere in here. It's 3. And then the only other one we can't do is the C to E, and the rest of them just get filled in like so. So you're just filling the initial one. Now we're doing the final iteration, and we're focusing on E. So we're thinking, okay, can we get to A to B faster than 10 if we go via E? Well, if we're starting at A and we go via E, that's 5 plus the 4 to get us to B, and that's 9 in total, which is less than 10. So that would be 9, and put some brackets around it to show that you've changed it because it's improvement. A to C currently is 13, but A to E takes you 5, and then E to C takes you 7, which is 12 in total. You can do it from the graph like I did, A to E and then E to C, which is 12 in total, or you can look at the picture, right? And just look A to C. Okay, well, if we go via E, that's 5 plus the 12 to take us to, sorry, plus the 7 to take us to C, which is this 4 and this 3. It's easier if you look at the graph because that, or sorry, if you look at the table, because that tells you the numbers instantly rather than you having to find it. Likewise, A to D, so A to D is currently 15. If you go via E, that's 5, plus E to D is 7. That's an improvement because that makes 12 as well. Now, the E's obviously aren't going to improve, so you may as well fill those all in now because you can't get to E faster by going via E. That doesn't make any sense. This is still symmetrical, so those are going to change. And now we've only got these 4 to fill in, but there's actually only 2 of them. But again, because of the symmetry here, sorry, actually 3 of them on there. B to C is currently 3. Well, you're not going to improve on that because it takes you 4 to get to E, so that's not going to improvement. B to D is 5. You could go via E as long as there's a way to get there in 1, which there isn't, so that's going to stay at 5. Symmetry again, and then finally C to D is going to be 2 currently. Takes you 7 to get to E, so that's not going to be improvement either, and that would be the Floyd's done. Question 2 then is about this network here. It wants us first to get out, so this is the whole question, but first it wants us to complete this. So we start at 0, 0, and then the top numbers are the biggest number you can find to get here first. So obviously just 3 first, but this number here isn't 4, it's 3 plus 5, biggest number. This is just 7, it's the only way to get there. You probably should have checked 7 plus 0 before I put the 8 in, but whatever, it's still less than 8. So that's fine. This is just 9 because that's the only way to get there. This could be 10, or it could be 9 plus 1, or it could be 7 plus 4. The biggest is 7 plus 4, which is 11. Then copy the 11 down here, and then backwards, we're just going to do the smallest number we can. The only way to get there is -1, so that's 10. You could either -1 to get back to 9, or 9, or 7 minus 4. We should probably do first to 7, and then 7. And then this is actually forwards, right? So that would be the smallest thing to be. You can't, if you're checking the backwards one, this arrow is going the wrong way because you're following it rather than going backwards along it. So yeah, this is 9 because both of these make 9, and then this is 7 because it's the only way to get there, and then backwards goes to 0, and then we missed this one up here actually, so that makes 4. If you do that, and that's the whole thing done. Obviously 11 is the completion time. Do a histogram here. So we're going to start maybe with the critical path. We don't have to because it just says that everything has to be done as early as possible. But just by habit, maybe start with critical path. T takes 2 people, so it's 2 tall and takes up to 7. And then G takes another 4 hours and it only takes 1 person. Now let's fill in A, and C maybe because those are the other things we can start with. So I'll fill those in like that. They both take 2 people and take that many hours. We can start E, or B, I should say, actually, is the next one start, isn't it, after A? We can start B as soon as A is done. Now B takes 5 hours. It's only one person. So I'm going to put one box there, then follow it with a few boxes here, and still one more hour of B needs doing, so I'll put it down here. Always force it down as far as you can. Don't leave overhangs in your graph. So always force it down like this. And then E, I think, is the next one to think about. Well, that only takes 1 hour, but it does take 3 people. So we're just going to put that over there. But we do need to wait for B to get done. But also while waiting for B to get done, F needs to get done. And I just drew it here to make the graph look more pretty. But I mean, it's whatever. H also takes 3 people and 1 hour. So it's the same as E, basically. It gets done as soon as E does as well. And that'll be our entire picture like that. And 6 workers are required between 0 and 3 and 8 and 10. And that's done. Question 3 then. So we're going to start, this is the whole question again. We're going to start with Dijkstra. So we start with a 1, 0, and then just fan out in every way you can. So 23, 35, 41. Pick the smallest, that's 23. So that's going to be the second place we go, and it's worth 23. And then again, fan out all of the places you can go from the place you just put a number. So add 42 to this 23, add 37 to this 23, add 8 to this 23, and then look around all of the boxes that you've got information for. The smallest one is this 31, so that's the third place we go, value 31. Once again, fan out all the places. So 31 plus 30 to get you to there, 31 plus 28, 31 plus 45, 31 plus 43, and 31 plus 7. Even though you're going backwards, you're still allowed to do it, or it feels like you're going backwards, but you still have to do it. 38 is actually, it's important that you spot that one because 38 is the smallest we can go. 438. Again, keep going. We don't need to do the 7 because we've already been here. So you only go to the places you haven't been. At the start, that's basically everywhere. But now it's just going to be this one and this one is the only 2 that we need to go to that don't have already a completion number in them. And now look for the smallest. That's going to be this 59, it looks like. So that's going to be 559. We can follow this one. We can follow this one. We can follow this one. Don't need to follow those 2 because they take us to things we've already labeled. So we follow the 3 that I said there. Pick the smallest. One more thing to do there and there, I guess, will be our 2. Pick the smallest, put it down. We can still go backwards this 22 down to there, and we can go forwards to there. Those are the only 2 left here. So pick the smallest is going to be this one, is going to be 70. Nowhere to go from this one because we've labeled them all around. So therefore, this just must be the 9, and it's worth 100. Now, to find, so the length of the shortest path is clearly 100. To find the shortest path, I've never found out an actually efficient way of doing this. You kind of just need to work back from what you said. So 100 minus 32 is 68, so that's going to be the H. Then minus 7 gets the E, so it finishes JHE. And then how do we get to the 61? Well, it was the second one we did. I don't even remember. Was it 61 plus 30 to make 31? So C came before that, and then B, and then A. There's not really an efficient way of doing that. You just kind of need to look at it and make sure you find it. Maybe make a note as you go along underneath of what you think is going to win and hope that that's right. I don't know. And this doesn't seem to be a good method at all. Anyway, we're doing this for 1,000 times the number of nodes that we were before. So we just have to do this times 1,000 squared because it's order 2. And we get that many seconds. If we divide that by 60, we'll work out how many minutes it is because they asked us in minutes, and that'll be that done. Question 4, it's not possible to put them in 3 bins because if you add up all of these numbers, you get 132 plus x, which is bigger than 3 times 40. So even if x was 0, those would not fit into 3 bins of size 40. X can't be 0 because it's the largest number on the list. So x is definitely bigger than 23. And the fact that it is possible to pack in size 40 means that the sum total must be less than or equal to 160 because you can actually do that, which means x is less than or equal to 28. It's bigger than 23 because it's the biggest number of the list, so therefore that's our range of values for x. Good. The first bin packing algorithm. So okay, bin 1, we'll just put the 15 in. We can fit a 22 in that because that adds to, 37 or something. We can also add a 3, that takes us to 40 exactly. So bin number 2 needs to have the 9 in it and the 23. Now that's currently like 32? Well, x is way bigger than 8, so we can't fit x in there. So x has got to go in the next one. Now 5 can fit into here, even if x is 28. But of course 5 can also fit into there, so it goes in the first one it can fit in. It's called first fit bin packing for a reason. This now totals to 1437, so that's pretty close, but the 4 can't go there. It's just slightly too big, so it does go in with the x. Now 18 plus 4 is 22. Even if you chose the smallest x you can of 24, that's not going to fit, so 18 has to go down here. The 20 can go with it though. Now the 13 plus 4 is 17, so if x was 23, but x can't be 23, can it? It's got to be bigger than that. then you'd be fine in here, but you're not. So 13 has to go in bin 5. Can't fit in the others, of course, way too big. So that'll be that. And carry out a quick sort now. So we start with these numbers. I've bolded X because it's in the middle of them. Yeah, X, is the biggest number, right? It says right here. So that needs to go right to the start, and then you just write down the rest of the numbers in order. 5 is now the middle number. So you write down all the numbers in order bigger than 5, which is actually all of them except for that 4 and that 3. Keep those in the order they currently are, which is 3, 4. So you write down all the numbers that are bigger than 5, ignore the 3, keep writing down the numbers, ignore the 4, and then you write down the 5, and then the 3 and the 4. That ensures 5 is in the right place because you've just essentially shoved only the smaller numbers after it, so therefore it's in place. Now I've got two things to pivot from, the 4 and the 23. If you've got like this where you've got a median that's in the middle, just round upwards to the number on the right. 4 is clearly needs swapping with 3, and then the 23 needs writing ahead of all of these because it's bigger than all of them. So it goes there. We now pivot from the 18 and from the 3, I guess, but that's clearly in place. 18, we just write down the 22 first, and then we have to write down the 20, and then the 18, and then the 15, 9, 13. So just writing them in order like that. Then pivot from the 9 and the 20, and we just keep going, right? And it works out pretty nicely in the end, and we end up with this here. Okay, now we're going to do first fit decreasing bin. So bin 1 goes X, bin 2 goes 23, bin 3 goes 22, bin 4 goes 20. This is why it is a slightly more efficient way, because it splits out the really big numbers. So then you can fit in the smaller numbers in hopefully a more efficient way. Anyway, 18 clearly can't go with X, because X is bigger than 22. It also can't go with 23, so it has to go with the 22. 15 apparently can't go with the first bin. It can't go with X. So that means X must be bigger than 25, otherwise it could. So you put the 15 here, but then the 13 apparently can't go with the X either. So X has to be bigger than 27, and the only thing in this list bigger than 27 is 28. So therefore we'll have X as 28, and we'll be done with that question too. Our next question here asks us first to consider pairings of relevant nodes. So this is when we find, we find all the odd nodes and we consider their pairs, and we find the shortest way to repeat roots. Now this question has a bit of a trip, which is that you must start at F and you must finish at J. Now finishing at J is great because J is an odd node, so finishing it means that you don't have to consider it as an odd node because it's essentially not one if you finish there. Now the problem is with F is that it's even. So if you start at F, F is therefore turned into an odd node, because you immediately have to leave F, and now it's only got 3 things to do. So F is actually an odd node in this case, even though it has 4 arcs. It's actually odd because you're starting at it, because you're forced to start at it, which is terrible, but whatever. So the odd nodes in this picture, if we're starting at F and ending at J, G, that one's clearly odd. We've got F, as I've already said. We've got C, which is over here, and we've got D as well here. Those are actually the odd ones. All the others, if you look, are even. Including J, because you're finishing there, essentially. So now let's just consider the pairings G, F, and C, D we can look at first. You just look in the table. G to F is 28, and C to D is 82. So you add those together. Then we consider maybe G to C and F to D. Again, look in the table, find them. And then the last pairing is this. You select the shortest, and then you actually have to look here, because this isn't necessarily just going from G to C, right? In fact, you can't go from G to C. So when we think about the roads that need to be traversed twice, we need to actually think about how are we making this 59? How are you getting from G to C in 59? Is it just this plus this plus this? It looks like it could be. So it's just G to A, and just add them up, A to B, B to C. And then F to D actually turns out to just be F to D, this 22 here. So those are the ones we have to do twice, and the total length is just the total network plus this 81, and we'll get to 504 as our answer there. So keeping on with this question then, we're asked to do prims on this table here. We're starting in A, so we'll cross out the A row and call A the first. And now look down this column, what's the smallest number? This 8, taking you to G, so G is the second. Cross out the G row and say A to G is first. Then look down the A and the G. Maybe look down the A, find the smallest number, that's 31. Sorry, no, it's not, it's 20. And then look down the G column, is there a smaller number? Nope, so this 20 going to F will be the next one. Cross out that row, A to F is next. Then look down the A, the smallest one is this 31. Look down the F, 22 is smaller. Look down the G, nothing smaller than 22. So 22 takes us to D, that's the next one. Cross out D, call it number 4, F to D, and then just keep going with that strategy. Look down the A column, find the smallest, then look down the next eligible column, then the next, and the next, and just see which one the smallest is row by row, and just keep on keeping on with that tactic, labeling all the things on the top just so it's super clear what you're doing. And eventually you'll end up with this. And at this point, actually, what I did was I decided to add up all the numbers that I found as I went along. So maybe the best tactic would be to write, when we were way back there, write down an 8 underneath this, because that's the one we found. Then write down, what was the next number we found? Was it a 20? Write down a 20 underneath that, and so on. And then you can add them all up. Now, it hasn't directly asked you to do that, but it's very useful for something that we're going to see at the end of the question. So the total is 141. I'm just going to say that just now. Anyway, then it says use nearest neighbor starting at G. So from G, the nearest one we can go to is A. Only takes 8. Again, and I'm actually going to, because it says find the lower bound, sorry, because it says find the upper bound now, I'm actually going to count it up as I go along because I am actually being asked to. And then from A, the smallest one is F. That's worth 20. And then from F, now you're only looking down one column at a time. That's the key thing here. But you can't go back to A, and you can't also go to G. The next smallest is D, which is 22. And then look down the D column. Don't go back to one you've already found. Find the smallest number, and so on. Add them all together at the end, of course. And we find this root, and we also find we have to go back to G, of course, at the end. So from E, which ends up being the last one to go to, you just have to take the hit and use this 87 to get yourself back to G. And you end up with 271 as the upper bound. Now it says by deleting G and all of its arcs. And this is why I found this total of 141 back here, because this is a spanning tree that includes all of them, the minimum spanning tree. So if we just delete G, all we'll end up doing is taking away this 8 that takes us to G. All of the others will still be there. So if we just do 141 take away 8, we're going to end up with a minimum spanning tree that doesn't involve G. And now to find a lower bound for the entire root, let's just add in the two smallest ways to get to G, and that's 8 and 23, and we'll end up with 164 as a lower bound for this. That might not be feasible, but it's a lower bound. Now, Pete decides to take the root he found in C. So again, we're going back to C. This is the thing we found via his nearest neighbor. Interpret the root in terms of actual towns. So G to A is actually just G to A. That's worth 8. Then A to F was worth 20, and that's just actually A to F. Now, F to D is 22, which is actually just F to D, so we go to D next. D to B is 65. Now, D to B, you can't even go. So now we have to study this and find how this table got us from D to B in 65. And I think it ended up being this, if I'm not mistaken. It was G to A to B is worth 65. So then we get to B actually going along those towns there. Now, B to C is 17. Again, is that just there? That's just there. So that's C there. Then to J is just the 10. So that's perfect. And then to H is just 12. So that's perfect as well. Just go to H. And now to E. H to E is clearly not just something we can do, I don't think. So we have to find, how do we get from H to E into 30? Pretty obvious. It's just this, then this. So that's go back to J, then to E. And now from E to G. This took me a long time to stare at, and I'm not going to find it again, so I'm just going to write it in. JCBAG. It was JC to B to A to G. That's the route that apparently gets you that 87. It's just a case of staring at it until you find it, and writing down all the places you go, and that'll be our route there. Now we need to draw an activity network. This is quite a complicated one to draw, hence why it's worth 5 marks. Needing the minimum number of dummies. So ABC obviously to start. D comes out of A, obviously. Now, E comes out of A and B. You could dummy up to A or down to B, but I noticed that something else needs A, B, and C. So if I dummied up to A, I would just have to dummy C up to A as well, and I don't really want to do that. So I'm going to dummy down to B, and then later I'm going to dummy up to B. And I think that's probably going to be more efficient, because if I dummied all them to A, then this D and this E would then have to dummy to each other, right? Rather than just finishing at the same point, because they don't start at the same point. So that seems probably a better way of doing that. But again, that's really hard to see in, in advance. So just get a pencil and paper and just try lots of different things. That's the key idea here is if something's not working, turn a dummy around. If you think you can minimize the number of dummies more efficiently, turn one around, put things in slightly different places, and it might end up being better. We need F coming out of D and D, which is why it was best for me not to start those in the same place. So F comes down there, maybe. Next, we need G coming from A, B, and C, so we'll dummy C up to that to make G come out of it. But something else needs F and G, so we need to put those in the same place to end with, and that's H coming out of those. And now I and J need D and E, so they need to come out differently from there, like this. K, annoyingly, needs all of them, right? K, G, I, and J. So that needs to come out of here, but then also link up with these two. So I think I need two dummies to get me somewhere in there. And then I can say that's K coming out there. And then maybe we still need, what do we still need here? We've got the H coming out of G, F and G. I said that one before, didn't I? And then from the I, we have an L, and I think that's the whole thing done quite efficiently-ish. And that'll be 5 marks. It's kind of fun though, I think, to do this with pen and pencil. Not so much in PowerPoint, but with pen and pencil, finding some areas is good. Anyway, BEIL is obviously the critical activities. It's the ones that have no float time. The float time of F is 2 hours. State the duration of F. Now F, looking at this, has to start after D and E. So F can only start here, earliest, because that's after E. And it also has to be done by the time H starts. Now H doesn't have to start here because of this float time. So H could start at 18. So therefore, F, the one that we're talking about, has to finish by 18 because that shoves H to as late as possible to finish by 24. So F takes up some space in between here, but it only takes 2 hours. Sorry, the float is 2 hours, which means the time must be 4 hours, and it goes 4 and then 2 float, and you can put the float wherever you want. Now J takes 8 hours apparently, and K takes Y hours. The maximum possible float for K. So again, let's think this through. The best start time for K, because it takes F, G, I, and J, I being the critical one. The best time K could ever start is at 19. Of course, it has to finish by 24. So that's 5 hours in total it could be using up. If its float time is, if the time it actually takes, we're talking about K here, if the time it actually takes is Y, then if it's got this 5 hour window to do it in, and the time it takes is Y, that means the float will be 5 minus Y. State in terms of X and Y the total float for J. Now J needs D and E. So I've just drawn K in here. That's the box that it kind of, I was drawing it with my mouse there and I forgot that I just put it on there. Anyway, J is, best start time is 12 apparently because it only needs D and E. So its best start time is at 12. It's obviously got to be done by the 24, except K has got to be done after it, right? Because K uses J. So, okay, let's just pretend for a second maybe that K took 1 hour and you shoved it right at the very end, that 1 hour there. That means that the one we're talking about, which is J, could finish only at 23. So you'd have a gap between 12 and 23 to do it. And then it would take you'd have a 9 hour window, and you just take away the amount of time it takes you, X, in the same way that we did 5 minus Y earlier. But of course, K could take 2 hours, and then it would suddenly be 8 minus X, or 7 minus X, depending on how long K takes. The formula will just be that 12 hour gap, that 12 hour window, minus X, minus the amount of time that floats, just like we said this one was, but then also minus the amount of time that K takes. Because it could take 1 hour, so we take away 1 from that window, or 2, we take away 2 from that window, or K could take 3 hours, take away 3 from the window. So likewise, it's just K, 12, take away X, take away Y. And the last question we have is the simplex algorithm question, of course, because we are always going to get one. The objective here is to maximize the profit, which is £8 times the paperbacks, which are defined to be X, somewhere here, there, plus 20 times the Y, plus 40 times the Z. So that's the profit. That's what we're maximizing. Let's put the restrictions in order that we read them. So 4 times X plus 8 times Y plus 15 times Z has got to be less than 150 hours, but 150 hours is different to minutes, right? So 150 times 60 to get this in minutes as well. You could write these in hours, but I think it would be more annoying to do it. Likewise, underneath, we want 1x plus 5y plus 12z to be greater or equal to 60, lots of 60. And then underneath here, we want x plus y plus z to be greater or equal to 1600. And then here, we want 3 times as many x's. We want 3 times as many paperbacks as hardcovers. Yeah, 3 times as many x's as hardcovers. But that means you put the x's on their own and do 3 times the hardcovers. Because, you know, if you've got 3 papers, 1 hard, that means 3 is greater or equal to 3 times 1. So you just put the 3 on the other side like this. And I think this would be all the conditions. I'm going to rearrange those slightly. They all need to be positive, I guess you could also say. Just going to multiply those out to make this here. And now, whenever we're less than or equal to, we need to add in a slack. So we'll do that just there. We're going to rearrange the profit to make it equal 0, of course, because we just want to equal a number every time, whether that's 0 or not. Whenever it's less than, we need to add a slack. Whenever it's greater than, we need to add in a slack and take away a slack, to get it down to 0, and then add in an artificial. So here we also need to take away a slack to get it down to an equals, but then also add in an artificial, call it a different letter. And then here, that's just so that we don't have to add in an artificial, let's put the number on the greater than side. So let's do 3y minus x, I guess, to get minus x plus 3y is less than or equal to 0. And then we just need to add in a slack. And that saves us an artificial variable if we do it like that. And now this I thing is just minus the sum of the artificials that you have. That's just always what it is. And you can rearrange, of course, these two lines for these two artificial variables to get this. So everything up to here is just A1, and then this is just A2. So you put those together, and again, make this the same as all the previous lines you've got, where you just want the random number over on the other side and all the actual stuff over on this side. And then finally, we're ready with all of that stuff as it is, all of our things there. We're ready to set up the Tableau. Saying the word Tableau, of course, is the only fun thing about this entire method. But okay, what we need along the top is, of course, all the slacks and all the artificials that we involved. Along the side here, we just need all of the positive slacks or artificials from here. So S1, A1, A2, and S4. Those are the positive ones. We don't want these negative ones. And we ignore the I line because that's already there. So we have the positive ones only. And now we just fill in the coefficients, right? So this first one is this row here is the one that has S1 in it. So that's this row here. So that goes 4, 8, 15, and then 1, and then a bunch of zeros because there's none of those S's or A's in it, and then 9,000. Then the one that has A1 in it is this one here. So that's going to be 1, 5, 12, and then there's 0 S1s, but there's minus 1 S2s, and then like so. And then the next one is the one with A2. That's this row. So hopefully that's fairly self-explanatory now. And you keep going with that method like this. And then the P row is this one here. So that's going to be minus 8, minus 20, minus 40, lots and lots of zeros after that. And then the I row is finally this one here. And we end up with our initial Tableau filled in. And now it wants us to actually do an iteration of Simplex. So what we're going to do is we're going to start by picking the smallest value of in this P row, which is this one here. The smallest negative is that one there because 56 is bigger than the other two. And now what we're going to pivot from is by working out the thetas. We can do 600 divided by 3, and we can do this divided by that, and this divided by that, and this divided by that. And we'll pick the smallest positive number from that list, which is this 200, and we'll therefore pivot from this square there. So what we want to do is we want to make this square into a 1, and all of these into zeros. So clearly to make this into a 1, we're just going to times this entire row by a third, or divide it by 3. And also this S3 is now going to be solved for because it's going to be a 1 here. So this becomes an S3 over here. So divide that entire row by a third, or sorry, times it by a third or divide by 3. And all those numbers go down a little bit. And this one crucially becomes a 1. And now, like I said, we want to make all of these zeros. So we're going to want to say, okay, this is currently 1/11th. So let's do 1/11th minus an 11th of this will take us to 0. So these numbers just stay the same as they are because we aren't solving for those. But this is going to be a 0 because if we do this entire row, which I'll call if we do this entire row, which I'll call little r2, and take away big R1, which is this row now, it's the modified little r1 from before. This is little r1. Big R1 divided by 11. So this divided by 11 is obviously an 11th. And then this row's input is 1/11th, take away an 11th, and we get to 0. And so up here, 0 take away 0, well, 0 take away this 0 divided by 11 technically is still 0. 4/11ths take away this divided by 11 is still 4/11ths. 1 take away this divided by 11 is still 1. 0 take away this divided by 11 is minus a 33rd. And minus 11th take away this divided by 11 is that. And then finally 0 take away lots of zeros is 0. Or not finally, because this take away an 11th of that is apparently that. They've also got rid of the A columns, which is nice because it saves us some work and we didn't need them anyway. So we get down to this. Then the next one, so how do we make this into a 0 from this number here? Well, again, if we divide that by 11, we get 1/11th. But then times it by 12, we get 12/11ths, and then add it to this, we'll end up with 0. So I think we need to do this row, which we'll call little r3, plus 12 times this number divided by 11 to make it into a 12/11ths, add them in to make it go to a 0. And then you just do it very carefully. 0 take away 0 is still 0. Oh, sorry, 1. Sorry, 1 take away some amount of 0 is still 1. 7/11ths take away some amount of 0 is still 7/11ths. 0, 0 is all good, so that's still 0. Next, more complicated one, I think, is it this 0 add in 12 elevenths of that, I guess? Um, is that what happened there? S1, yeah, sure. And the next one is going to be this 1/11. So it's just 1/11 more than that is, right? Because it was 0 lots of it. So that's 1/11 of it. This is 0 by design. There's two zeros, make more zeros. And then finally, this number um, plus 12/11 of that number is apparently that there. I'm just using fractions like this because otherwise they won't fit in my boxes. Anyway, you get the idea. The next one is actually very hopefully exactly the same thing as the row above it. So you just keep doing exactly what you just did. And then for the very last row, we want to make, sorry, the very last row being this one here, we want to do this because, of course, we just need to make this 12 into a 56, essentially to make the whole thing work the same as it was before. And you eventually end up with these numbers if you just do exactly the same strategy as you were doing before. And that will be all of the marks got there. Just be super careful when you do it. The maximum profit can be read by this number here. The number of hours the machine will be used while you're using 1,125 X's, and they took 4 minutes. That's 4 over 60 hours. Sorry, those took 1 minute to bind. We're being asked about binding. So 1 over 60 to bind. Then we have 375 Ys, which take 5 out of 60 hours to bind. And then we have 100 Zs, which take 12 out of 60 hours to bind. Add those together, we get 70 hours. They might not learn this. Interestingly, the only thing you can say here is because they might not sell all the books. That's the only thing you can correctly say there for that question. They just, the fact that you can make this profit if you sell all the books doesn't mean that you will sell all the books. So yeah. Excellent. That's the whole paper done.